Okay, so this is a video to review modules 2 and 3 from the OCR specification. So before we get started, I'd like to give you some advice about how to use this video. So first of all, I provided a link to a template you can fill in as we work through the video, which is in the description of this video. So I recommend downloading that first of all. But the second thing is, this isn't a tool to go about using at the start of A-level physics or like halfway through. This is a tool to be using at the end when you're going back and revising A-level physics in preparation for the final exams. The next thing is, once you've downloaded the Word template, it's really important that you go through each section before you watch the video on it, because you really need to find out how much you currently know and what improvements you need to make in each of the different sections, which you will only find out if you try and work through it first. The third thing is, this isn't a process you should go through only once. So having gone through, filled in your answers and improved it, that doesn't mean this resource is now useless. This is something you should do repeatedly over time. So maybe in a couple of weeks, come back and do the same process again. That's how you will gradually improve your knowledge. And just another thing to share with you is a resource I've created to help you learn the knowledge or the definitions that go with the topics. And again, there's a link to this in the description to the video. It's a tool that you can use to do language learning, but it's also great for learning definitions too. So there's a link for that. And again, like everything, if you want to improve your knowledge, you have to practice, and with definitions, doing it every few days will be incredibly beneficial until you can recall it with absolutely no effort and it comes straight out. Okay, so let's make a start. So we're going to start off looking at Module 2, looking at units, and then we'll progress on to Module 3, looking at mechanics. Okay, so these are the things the specification says that you should be able to do in terms of SI and base units. So what I'd like you to do is, on the template, what I'd like you to do is have a go and see if you can complete section 2.1 SI and base units, or do as much as you possibly can. Then we'll take a look through that section. Okay, so I'm going to assume that you've paused the video and you've been through to complete each section. So let's first take a look at these 7 base units. So they're in no particular order. These are just the order that I remembered them in. Okay, so these are the 7 base units, and you will notice I put one of them in purple because I sat here for a few minutes going, oh, what's the 7th one? So I've put that in a different color, just so that when I'm going back over this, I know that was the one that I was forgetting, and that's the one I should be practicing. So use color as you're going through these things. Okay, so those are our 7 base units. So the first thing we're going to express in base units is magnetic flux density, and this is why I said at the start that you shouldn't use this video until you finish the course, because anyone who's not done the second year will not have a clue what magnetic flux density is. So the equation I'm going to use is F equals Bill, the force on a conductor. We want to know the unit for flux density, so let's make B the subject. Let's sub in the units for all the different properties, and then for newtons, we're going to substitute in kilograms meters per second squared, giving us the base units of flux density. We can do the same process again for spring constant as well. So we're going to use the mathematical version of Hooke's law, make K the subject, sub in the units, turn them into base units, and we get kilograms per second squared. Okay, so then for C, recalling the SI units for the properties, there's a section on the Memrise tool for practicing the SI units in mechanics. I'm not just going to go and list every unit of every topic right now, and I'll do the same thing for the other topics as and when I make those videos too. So we're going to jump straight onto the homogeneity of equations using base units. So the first thing we're going to look at is showing that UT and half AT squared both have the units of distance, because you should know the equation S equals UT plus half AT squared, and you can only add stuff if they have the same unit. So we should be able to show that. So UT, fairly straightforwardly, U is a velocity, so as you know, meters per second. T has a second, so multiplying them together, you get meters. Half doesn't have any units. Acceleration is meters per second squared. Time squared is second squared, so that gives us meters as well. So they both have the unit of meters. Then what we're going to do is we're going to show the equation W equals Fs cosine theta is homogeneous. So first of all, work done is measured in joules, and a joule you should know is a Newton meter or a kilogram meter squared s to the minus 2. Fs cosine theta, F is a force, S is in meters, cosine theta doesn't have any units, which is why I just put a 1. And then we can see that we end up with exactly the same unit, so we show it's homogeneous. Okay, so then looking at our prefixes, all the way from femto, our size of the nucleus, kind of up to tera, getting onto the large scales. So we'll go through the symbols first, so you know how to recognize them when you are given them in questions. So those are the symbols you'll see before the unit. And then the powers from minus 15, most of them go up in 3s until now. Centi is minus 2 because centimeter is 100th of a meter. Deci is minus 1. That's why a decimeter cubed is the same as a liter. And then again, we start going up in 3s until we finish off at 12. Okay, so that finishes 2.1. Let's move on to take a look at module 2.2, looking at measurements and the uncertainties. So again, these are the things that you should, the specification says you should know or be able to define. So again, what you need to do is work through section 2.2 and see if you can define what each of the things are. And then we'll take a look through it as before. Okay, so let's take a look. So a systematic error, this is an error that is predictable. What a lot of people will write here is it has to have, the error is the same value every time. That's not exactly true. It just has to be a predictable error, which means we can remove it from our measurements, which is called calibration. So it's a predictable error. Random error is an error that you cannot predict, and the only way you can deal with random errors is by taking repeat readings and getting an average. That's the only tool really that we have available to us. Okay, so then we want to define precision, resolution, sensitivity, and accuracy. So precision is the number of decimal places to which a measurement is stated, whereas resolution is the smallest division on a measuring instrument. So they're not necessarily the same. Sensitivity is the smallest detectable change in conditions using an instrument. So I don't know, if you're using a thermometer, it's the smallest temperature change that you can measure. And accuracy is how close a measurement or a calculated value is to the true value. Moving on to look at uncertainty. So the uncertainty in a measurement from an analog measuring device, like a meter ruler or a thermometer, protractor, something like that, that would be half of the resolution because you can kind of interpolate between the divisions. On a digital, however, the uncertainty is just the resolution of the measuring device because we have no idea where it was between the values. And if we have an average value, that must mean we had repeat readings. So we can calculate the uncertainty in that average using the range of the repeat readings divided by 2. So the first two are predictions about what the uncertainty is. If we have repeat readings, we can actually calculate what the uncertainty is, which is better. So to find the uncertainty in a gradient, you need a graph with error bars on it. And what you do is you draw a line of best fit and a line of worst fit. And a line of worst fit is essentially the worst line of best fit that still goes through the error bars, whereas your best fit, you're trying to get it close to as all the points as you can. And once you've done that, you find the difference between the gradients of the two lines. That will be the uncertainty in the gradient. It's the same process with the intercepts. Again, you draw your lines of best and worst fit or use the same one. and then you find the difference between the intercepts of the two lines. Those are your uncertainties. Okay, so moving on to section 2.3, scalars and vectors. So starting to bridge into mechanics. Again, what you should do is pause the video and go through and check through each of these, see if you know them. So work through section 2.3 and then go through and correct your answers. All right, so let's take a look. So scalar, a property that has only magnitude, so things like speed, distance, temperature, energy, all of those kind of things. And vectors are properties that have magnitude and direction, so forces, velocities, accelerations, momentum, that kind of thing. Okay, so just a little thing at this point that crops up quite a lot. So just because something can be positive and negative doesn't make it a vector. So both scalars and vectors can be positive and negative. For example, temperature is a scalar, but it can be positive and negative. Energy can be positive and negative. So be a bit careful with when you're identifying whether things are vectors using signs. Okay, so the next one, several of the questions or the sections of this, I'm going to ask you to start thinking about and generating questions. So you can start thinking about where you would apply the various skills. So you will not come up with the same question as me. I'm just going to give you an example every time. And every time you use this task, try and come up with another question and another worked solution. So you're building up a bank of scenarios in which you might apply the skills. So my example is a person running towards the front of an aircraft at a relative velocity of 5 meters per second. The aircraft has a horizontal velocity of 40 meters per second and a vertical velocity of 30 meters per second. Calculate the velocity of the person. So first of all, we are adding vectors. So there's the vector of the velocity of the aircraft. There is the vector of the velocity of the person. Now, at the moment, we're not in a very good position to add all these together because all of the vectors aren't parallel or perpendicular. So what we're going to do is calculate the resultant of the aircraft's velocity, then we can add them together. So the person's velocity is just going to be v plus 5. And v is going to be the square root of 30 squared plus 40 squared using Pythagoras. And then we add those together and we get 55. So there's where we've added perpendicular vectors. Here's where we've added parallel vectors together. Okay, so then next one, using a vector triangle to calculate the resultant of any two coplanar vectors. Coplanar meaning in the same plane. So again, what I'd like you to do is come up with a question and try and put it in a context that will allow you to show using this skill. So the question I came up with, I'm going to be thinking about ships. So we've got a ship engine providing a forward force of 100 kilonewtons. Sail is producing a force of 50 kilonewtons at 30 degrees because it has to point towards the wind. Calculate the resultant force. So with vectors, we always add them tip to tail like this. So those are the two vectors. And we know the 50 is at 30 degrees to the 100 kilonewtons. So if we want to find the resultant, effectively we want to find the green vector that goes from the start to the end. We also know an angle inside this section. So what I'm going to do is I'm going to use the cosine rule because I know two sides and the angle between them and find the resultant force. Okay, D, resolving a vector into two perpendicular components. So for this one, I ask you to design a question that resolves vectors into directions other than horizontal or vertical, because that's the one you'll use the most. So let's do something different. So the easiest scenario to come up with would be on a slope where it's slightly different. On a slope, we resolve parallel and perpendicular to the slope. So in a nice general case, this is what it looks like. I'm going to add in some more lengths to help us understand how the resolving works. So that's what we've got there. So we've got the weight force, which acts vertically, and we want the components parallel and perpendicular to the slope. So we're splitting the vector into two perpendicular components. And then the side perpendicular to slope is the adjacent angle to the theta, so therefore it's cosine. The parallel to the slope is opposite the angle, so it's mg sine theta. So that would be us resolving, but not horizontally or vertically. All right, so getting into some kinematics. Again, as before, I'd like you to work through the section on kinematics and then we'll review it. So have a work through section 3.1 part 1 and then we will review it afterwards. All right, so displacement first of all. So displacement is a vector describing how to go to a point in space from the original position at 0, 0. And then velocity kind of comes from that. So velocity is the rate of change of displacement. And then instantaneous acceleration, which is often abbreviated to acceleration, is the rate of change of velocity. So usually we don't put the word instantaneous in, we just say velocity or acceleration, but if we were giving it its full name, it would be called instantaneous velocity or acceleration. Okay, so sketch displacement, velocity, and acceleration graphs for an object traveling at constant velocity. Well, if it's a constant velocity, acceleration is 0. The velocity is constant or a horizontal line, and that would mean that the displacement time graph is a straight line because velocity is the gradient. All right, so nice and easy. Sketch displacement, velocity, and acceleration graphs for an object traveling at constant acceleration. Okay, so constant acceleration will be a horizontal line. That's going to mean the velocity versus time graph is straight line because acceleration is the constant. And that's going to mean displacement versus time is going upwards because velocity is increasing, therefore the gradient of the displacement time graph must be increasing. Finally, sketch displacement, velocity, and acceleration graphs for an accelerating car. So the faster a car gets, the bigger air resistance becomes. So the acceleration is going to decrease until it gets to 0 when all the forces are balanced. That's going to mean the car reaches a terminal velocity like this. And that means our displacement versus time graph is going to become a straight line. So initially the gradient increases, but then becomes a straight line. Okay. So now what we're going to do is describe how we find various properties from the graphs. So if we have a linear or a straight line displacement versus time graph, velocity will be just finding the gradient, but we should find it over as much of the graph as possible to minimize percentage uncertainty in the measured value. So describe how we find acceleration from a non-linear velocity versus time graph. Well, the first thing you do is draw a tangent to the graph where you want the acceleration, and then you find the gradient of that tangent. Displacement from a velocity versus time graph, we need the area between the graph and the x-axis, and if it's above the x-axis is positive displacement, if it's below the x-axis it's negative displacement. Use the acceleration versus time graph to calculate velocity. So, first of all, we're going to use an area method, and usually when you're using a graph, you'd use some sort of approximation method, maybe counting squares or using a trapezium rule. And then we want the final velocity, so what we're going to do is add our area to the initial velocity, because the area is equal to the change in velocity. So that's how we get our final velocity. All right, so next moving on to the section on linear motion, we're now going to use the information from the previous section to get some of our equations of motion and then think about how we can use them in practical work. So again, work through this section, do as much as you can, and then we'll review it. All right, so now you've had a go at this, let's look at using graphs to prove these first two equations. So there are different ways of doing it, but these would be mine. So you should know that the change in velocity is the area under an acceleration graph, and if acceleration is constant, that looks like this. And so that gives us that the change in velocity is equal to AT. The change in velocity would be the final minus the initial velocity, and therefore we end up with the equation v equals u plus at, which I'm going to call equation 1 so I can use it later. In terms of getting the next one, so now we're going to use a velocity versus time graph, but again we're going to use the area under it to get the displacement. So this is a trapezium, so the area is the average of the two sides multiplied by the base. So the average of the sides is half v plus u, the base is t, so we get s equals half u plus v times t, which is equation 2 and our second one that we were trying to derive. The next three all just come from using those two equations. So the first thing we're going to do is substitute equation 1 into equation 2. So replace u with u plus at, sorry, v with u plus at. Then we can work through the logic and you end up with s equals ut plus half at squared. We can do a similar thing now, except we'll rearrange equation 1 to make u the subject, now substitute in for u. We end up with the equation that most people forget about, and if often isn't on the equation sheets, s equals vt minus half at squared. And then finally, what we're going to do is we're going to make a substitution for t this time. So make t the subject, substitute that into the other equation, and we end up with v squared equals u squared plus 2as. Okay. So now we're going to start thinking about how we can actually make measurements of velocity and acceleration. So often we use a light gate as a way of measuring velocity and acceleration. So first we'll look at how we can use them to measure velocity. So what we can do is we can measure a length of card and you fix it to the top of the trolley and you make sure all of the card is going to go through the light gate. And then we use a data logger to record the time it takes for the car to pass through the light gate, or the time that the laser is broken. And from that, what we can do is we can calculate the velocity of the trolley, assuming that it was constant as it passed through. We can also use light gates as a way of measuring acceleration, or at least average acceleration. So we're going to go through the same process, except we're going to record the time taken for the car to pass between the two light gates, as well as the time taken to pass through each light gate. So the time taken to pass through each light gate gives us the velocity at the start and end, and the time between them allows us to calculate the acceleration from those readings. Okay. So now we're going to draw graphs of a motion for an object in free fall. So free fall means acted only by the weight force. So that would mean the acceleration is minus g, because if it's just the weight force, that's going to give you an acceleration of minus g. Velocity, therefore, is going to look like this. We didn't say we started at 0 velocity, so why would we draw that on a graph? And then our displacement is going to look like this, the gradient becoming increasingly negative. And then describe an experiment to determine g, and it should be something you can do in a normal school lab, but you want a method that will make it as accurate as possible. So the best tool that you have is the magnet and trap door setup. So what happens is when the ball is released at the top, it tells the timer to start timing, and when it closes the trap door at the bottom, the orange part, it tells the timer to stop timing. So it very accurately measures time, and the equation we're going to use is s equals ut plus half at squared. So let's actually break it down. So we use this as a method of getting rid of any error starting and stopping the timer at the right time, which you would have if somebody was using a stopwatch. And we'd also use a very small surface area ball to try and minimize any air resistance impact. So that's how we're going to make it as accurate as possible. Then what we have to do is measure the time at different heights. So I'm going to use 20, 30, etc. up to 80. And I'm going to repeat each measurement twice. So whenever I time anything, I'll get 3 values of time for the same measurement. And when we get the average of that, that helps us reduce any random error. So once we've got our readings, we plot a graph of height against time squared. We would measure the gradient of that graph, and we would multiply that gradient by 2 to give us what G is. And it should be somewhere around 9.81 if we've done it accurately. Okay, so calculate the distance required to stop a vehicle using thinking and braking distance. So thinking distance is how far you travel while you're trying to process things and haven't applied the brake. And braking distance is how far you travel once you have applied the brake. So for the thinking distance, A equals 0, so S equals UT, fairly straightforward. And then the distance when you're applying a force, so the acceleration is going to be minus F of m, because the force is in the opposite direction to velocity. And we also know that the velocity is going to become 0 at the end when it's stopped. And that allows us to get an expression for the displacement in terms of the mass, the initial speed, and the force. And then if we want an expression for the total distance, we can calculate that by adding those two terms together. Okay, so next section, looking at projectile motion. So projectiles use all of the stuff from Subat equations and then just add on a little bit more. So again, have a go at filling in this section, and then we'll take a look at how we'd explain each of those things. Okay, so first of all, why vertical and horizontal motion are independent. So projectiles, we say the only force acting on them is their weight force, which acts vertically downward. So if you calculate the component of the weight force horizontally, we can see that we'd be multiplying the weight force by cosine of 90, which is 0. So what that means is there's no force acting in the horizontal direction. So therefore, if we use Newton's first law, the velocity must be constant and therefore unaffected, which is why we can say they're independent. Okay. So again, at this stage, what I want you to come up with is your own scenario with a question, and then I'll show you an example. We want a situation where we've got constant velocity in one direction and constant acceleration in the other. So the scenario I've got is a poorly self-disciplined student is asleep in class. What a moron. The teacher throws a board pen at a velocity of 10 meters per second at an angle of 10 degrees to the horizontal. And what I probably should have said there is it's 10 degrees above the horizontal. And so if the student is a horizontal distance of 4 meters from the teacher, calculate how far above the student the teacher must release the pen to give them a nice whack and wake them up. So let's take a look at the solution to this. So I'm going to first focus on the horizontal direction. So the distance is or displacement is 4 meters. The velocity should be constant, and it'll be 10 cosine 10. Acceleration is 0, and we want the time here. So that's what I'll do. I'll get an expression for the time. Then what we can do is start thinking about the vertical direction. So we don't know the displacement, we want to find it. We know the initial velocity. We don't know the final velocity because there is no acceleration, but we do know acceleration and time. So what we can do is use S equals ut plus half AD squared, substitute in our values, and we get an expression for S as 0.70, and it's plus, which means the pen hits the student 0.7 meters above where it started. So the teacher needs to release the pen below the part of the student they would particularly want to hit with the pen in order to make it hit them. Okay. So that's projectile motion. Now we'll move on to non-uniform acceleration, because all of the Subat stuff we assumed acceleration is constant. And the most common cause of this would be drag or air resistance. So again, have a go at each of the sections in 3.2.2, and then we'll take a look. Okay, so Describe the key features of a drag force. So the first, we're going to look at the conditions that lead to a drag force. So essentially, it's caused by an object colliding with particles of a fluid. And by fluid, I mean either a liquid or a gas. We get drag from either of those two. And the drag force will always act in the opposite direction to the velocity, which is a useful thing to know. So now we can start thinking about the factors that affect the size. So there are two main factors, speed and area, because essentially both of these things will increase the number of collisions per second. And another thing, I put it in brackets there, is that the drag force is directly proportional to the area, but it's directly proportional to the speed squared. So it escalates very quickly at high speed. So now we're going to sketch and explain the graphs of motion for a falling object. So the acceleration starts off at minus 9.81 and then rapidly decreases to 0. And the reason it has this shape is because a drag is proportional to velocity squared. So the acceleration heads to 0 at an increasing rate. Then from that, we can get the velocity time graph that looks like this, heading towards terminal velocity, and our displacement graph heading towards being a straight line at the end. And the reason we get the terminal velocity section at the end is because the drag force is equal to the weight force, so the resultant force is 0, therefore acceleration is 0 and velocity remains constant. Okay, so now thinking about how we could actually measure or show and measure terminal velocity. So the easiest way to do this would be using a liquid in which the drag force would be a lot bigger than just normal air resistance. So what I'm going to do is get a nice big one and fill it with water. We could fill it with something more viscous if we want to, but water should be fine. And what we're going to do, first of all, is measure the distance between the divisions. So we're going to use the divisions as a reference frame for distance, but we need to know how big or how long that is. And finally, we're going to want to watch the motion over a period of time, so I'm going to use a slow motion camera like most of you will have on your smartphones. Okay, so we've got our setup. So what we're going to do, we're going to choose a ball with a higher density than water, so it sinks, and a cross-sectional area as big as possible so that it can fall down the tube but has a big drag force. And what we're going to do is we're going to record the location of the ball every 0.1 seconds and use our measurement from earlier to work out how far it's traveled at each point in time. So then we can plot a distance versus time graph. And if we want the terminal velocity, we'll find the gradient where it becomes a straight line. Okay, so those are all the scenarios with acceleration. Now we'll consider scenarios without acceleration, which we would call being in equilibrium. So again, what I'd like to do is work through section 3.2.3, seeing if you can define and explain the various things. Then we'll take a look. So first of all, the moment of a force is the product of a force and the perpendicular distance between the line of action of the force and the pivot point. So let's draw an example to show what that means. We've got a pivot on the left, a force on the right at an angle. The line of action is just a dotted line that extends the force arrow, and we want the distance perpendicular to the line of action, which is shown in green. Okay. So now we're going to define a couple and a torque. So a couple is when we have two forces with equal magnitude in opposite directions, but they're acting to rotate an object in the same direction. So they're both clockwise or both anti-clockwise. And the torque you get from a couple is a product of the force and the distance between them. So that would give you what the torque was. Okay, so now we know what a couple and a moment are. We're going to start stating what the principle of moments is. So the principle of moment states that if an object's in equilibrium, so it's not accelerating, the total moment clockwise is equal to the total moment anti-clockwise, but these are taken about the same pivot. And moments is very often tied up with finding center of mass and center of gravity. So center of mass is the point on an object where the mass can be modeled to be concentrated. So all the mass is at one point. And center of gravity is the point we consider the weight force acting from. And most of the time, those two are exactly the same location, because at most of the time we're in what we call a uniform gravitational field, where the field strength is constant. Okay, so next we're going to describe how we can actually find the center of gravity of an object. This is a very simple thing. We essentially just need an object to hang this off, and we need a plumb line, and we need a pen. So what we do is we're going to hang the object from a point, and we're going to use a plumb line, which is essentially just a mass on a string, to draw vertical lines downwards from the pivot. And once we do that, we then hang it from another place and draw another vertical line. And if it's in 3D, we do that step again, so we've got 3 lines. And wherever those lines intersect would be where the center of gravity is. Okay, so now what we're going to do is think about, again, coming up with a scenario to apply the conditions of equilibrium. So the scenario I've come up with is trying to balance a meter ruler with a mass hanging on it, and you can see that in the diagram here. And what we need to know is where to place our finger or apply the force F. So using our first condition of equilibrium, essentially using Newton's first law, we know the resultant force must be 0 if the acceleration is 0. So we know that F should be equal to 0.3 g. Using our condition of equilibrium about moments, we're going to take moments about the left-hand end at the 0 centimeter mark, and x is going to be the distance f from the 0 mark. So we've got the moments of the two weight forces in red, and then that's got to be equal to the moment of the force in green. You can rearrange that and solve x. So we'd have to place our finger under the 23 centimeter mark. Okay, so again, another question design, coming up with a scenario to apply the equilibrium triangle of 3 coplanar or same plane forces. The scenario I came up with is a parachutist at terminal velocity by thinking about the tension force from the cords attaching them to the parachute. So those two are at 20 degrees to the vertical. Calculate the tension if the parachutist has weight mg. So let's first draw a diagram of what the forces look like. So that's 3 forces, but they're not currently in an equilibrium triangle. The equilibrium triangle will look like this, with them all arranged tip to tail. And once we've got that triangle, we can work out what the angle is between the two tensions. Well, it's got to be 140. And then once we've got that, we can use the sine rule to figure out what the tensions must be. And it's an isosceles triangle, so the tensions would have to be the same. All right, so moving on from equilibrium to look at density and pressure. So again, have a work through section 3.2.4, and then we'll take a look. All right, so density, that is the mass per unit volume of an object, or the total mass divided by the total volume of the object is another way of expressing it. And pressure is the force per unit area, or the force divided by the area over which it acts. So next, essentially trying to figure out what the upthrust pressure would be on an object that is submerged. So the object is shown in red, and it has height x and cross-section area, we'll call it A, and it's a distance h below the surface, or its top is a distance h below the surface. What we're going to do is going to calculate the pressure on the top of the object, the pressure on the bottom, and find the difference between them to work out the upthrust pressure and then the upthrust force. So the pressure above the object would be due to the weight of the water above it. So the weight would be mg, and it's spread over an area A. Mass is going to be density times volume. So what we can do is cancel the A's, and we can end up with the pressure on the top surface is just the density of water times by G times by how far underwater you are. And we can repeat the process for below the object too, but instead of H, it's now H plus X. So then we can get a pressure difference, which would be responsible for the upthrust of rho, which is the density of water, G hex. And then what we can do is we can get an expression for the force by applying the pressure difference by the area, and we get the density of water times G times the volume of the object, which is the weight of water that has been displaced by the object. So that is essentially an expression of Archimedes' principle that the upthrust force is equal to the weight of water displaced. Okay. So now moving on to looking at modeling objects using work, energy, and power. So first of all, again, work through section 3.3.1, seeing if you can define each of these things and find the condition. All right, so now you've worked your way through. So work done is the product of force and displacement parallel to the force. We often calculate work done using W equals Fs cosine theta. So theta is the angle between the force and the displacement, but this equation is only a valid method if the force is constant. Otherwise, we have to use the area under a force displacement graph. So work done is often associated with conservation of energy. So the principle of conservation of energy states that energy can't be created or destroyed, only transferred. And then there's a slightly different principle, the principle of conservation of mechanical energy. So let's first explain mechanical energy. Well, it's the sum of a system's kinetic, gravitational potential, and elastic potential energy. So conservation of mechanical energy states that if there's no external force, so if there's no air resistance, no friction, anything like that, its total mechanical energy is constant. And the mathematical way to model conservation of energy or mechanical energy is usually in the form of this equation here. The work done is equal to the change in kinetic energy plus the change in GP plus the change in elastic potential energy, and those will be equal to 0 if there's no external force. Okay, so looking in a bit more detail at kinetic and potential energies, first of all, gravitational potential energy as well as kinetic energy. So again, work your way through this section. It should be fairly quick. Then we'll take a look. Okay, so kinetic energy is the work you have to do to accelerate an object from stationary, and you should be familiar with the equation half mv squared. Gravitational potential energy is the work you do against an object's weight force to increase the height of an object from a point that you've defined as 0 GP. And in mechanics, we usually use ground level as 0 GP, but we don't have to. And again, equation should be familiar, mgh. So again, you should have come up with a scenario to apply conservation of energy to kinetic and GP. So mine was, we've got a 4 kilogram ball traveling vertically upwards at 4 meters per second, another 2 kilogram ball traveling downwards at 4 meters per second. If they start from the same height and we ignore air resistance, which ball is traveling faster when it lands? So if we work through the logic, starting with our expression of conservation of energy, no external forces, so W equals 0, no shape changing, so change in EP is 0. Then we've substituted in expressions for the change in kinetic energy and the change in GP, remembering they're going to end up below their starting point, so the change in GP is going to be negative. And then we can cancel masses by dividing both sides by mass and do some rearranging, and we end up with v squared equals u squared plus 2gh. And you can see from this expression they have the same height, the same initial velocity, because the direction doesn't matter once you square it, so they're going to have the same final velocity when they hit the ground. Okay, so looking at power, section 3.3.3, again, work your way through here and then we'll take a look. Okay, so power is the rate at which work is done, fairly simple. There are two types of power used. Average power, which is the total work done divided by the time in which you did that work. And instantaneous power, often just called power, is the power at a specific moment in time, which we can know by the force that's being applied times by the velocity. And then efficiency we can get from either energy or power. So the form of it you'll be used to, useful energy output over total energy input, but we can also get it from power output and power input too. All right, so now getting into the materials section of Module 3, looking at springs first of all. Again, work your way through section 3.4.1, then we'll stop and take a review. So a tensile force is a force that acts to increase the length of an object. A compressive force, one acting to decrease the length of an object. Fairly straightforward. So Hooke's law we use to explain how springs behave states that force is directly proportional to extension up to the limit of proportionality. Okay, so then coming up with a scenario to apply Hooke's law. So the one I came up with is we've got a mass on a mass balance, and we've got two springs in parallel with spring constant K, and they're inside the balance and they decrease by a distance x. So what we want to find out is express K in terms of m, g, and x. So Hooke's law tells us that F is equal to the total stiffness constant times the extension. The force we've applied is the weight force. Two springs in parallel will have a spring constant of 2K, and then we can rearrange that to make K the subject and get mg over 2x. Okay, so next we're going to sketch some force versus extension graphs for springs and wires. So for a while, it will obey Hooke's law, and most springs and wires do, but then we'll go past the point called the limit of proportionality, and then we'll stop obeying Hooke's law. So most of them look a bit like this. So then we're going to look at techniques we can use to investigate force extension characteristics, maybe of rubber bands or polythene or something completely different. So the basic setup we're going to need is a clamp, a G-clamp, the material we're interested in, and some slotted masses. So the reason we need a G-clamp is to stop the system toppling over. And we're also going to need to measure the original length of the material using a meter ruler. Then what we're going to do is we're going to hang our mass on there and measure the new length or the extended length, and we'll use that to figure out what the extension is. And then we can add more and more masses so we can plot a graph of force versus extension for the material. So now looking at it in a bit more detail in terms of energy and also Young modulus. Again, work your way through section 3.4.2 and then we'll take a look. Alrighty, so first of all, elastic potential energy. So the work done to change the shape of a material from being underformed before. And then in terms of calculating it, if it's obeying Hooke's law, so elastic potential energy is work done, which is the area under a force versus displacement graph, because force is constant. And the area under the graph is going to be half Fx. But we can also express that as half kx squared or half f squared over k. All three of those equations will give us the same result. So then defining some new properties, stress, the force divided by cross-sectional area, so very similar to pressure really. Strain is the extension divided by the original length, and then ultimate tensile stress is the maximum tensile stress that a material can undergo. So now we're going to talk about Young modulus, which is essentially a measure of how stiff a material is. So first of all, defining it, it's the ratio of tensile stress to tensile strain. And we quote values from the straight line section of the graph. and we can calculate it if we know stress or strain, or if we make some substitutions, we can calculate it if we know F, L, A, and X. So then we can look at techniques we're going to use to determine Young modulus. So we could use a similar method to the one we used before, but typically we use a slightly different method. We'll use a vernier scale as a way of measuring the extension. So essentially how this works is you compare your test wire to a reference wire and directly measure the extension using the vernier scale. So again, we'd need to measure the original length, probably using a meter ruler. And again, we're going to need to clamp our system so it's not going to topple over, because this is probably all fixed to a G clamp unless you've got a clamp stand unless you've got something better. So then we're going to need much bigger masses because we're usually doing this for a wire. So I'm going to start with 1 kilogram and measure the extension using the vernier scale. Then I'm going to go 2 kilograms, 3 kilograms, etc., getting the extension for each. If we're going to calculate the stress, we're going to need to first find the area, and we're going to do that by measuring the diameter in a few different places and get an average diameter to calculate area. Then we can plot a stress versus strain graph and measure the gradient in the straight line section to find Young modulus. So we're going to look at the graphs for different materials. So I've used the same graph every time. I'm just going to look at the areas that indicate the properties. So first looking at ductile versus brittle. So ductile have a long region after the elastic limit, or a long plastic region, whereas brittle have a short or even zero plastic region of the graph. A flexible material, you get a large strain at a lower stress, whereas a stiff material, or a material with a high Young modulus, we have low strain even with a high stress. And then in terms of weak versus strong, weak have a small ultimate tensile stress, whereas strong have a high ultimate tensile stress. Okay. So finally, defining what we mean by elastic and plastic deformation. So to define ductile brittle, we needed to talk about that. So let's be clear what we mean. Elastic means when you stretch a material, but you don't go past its elastic limit, so it will go back to the same shape once you take away the force. Plastic means that once you take away the force, the material is going to be permanently deformed or damaged. All right, so final topic in mechanics, or module 3, Newton's laws of motion. So again, work your way through this, defining each of the laws, and then we'll take a look at each of them. All right, so first of all, Newton's first law. It's usually expressed as an object will remain in uniform motion unless it's acted on by a resultant force. But in a nutshell, what that means is velocity is constant unless a resultant force acts. Newton's second law states resultant force is equal to the rate of change of momentum of an object. And Newton's third law says every action has an equal and opposite reaction. And what that means is the force, when you apply a force to an object, the object will apply a force back, equal in magnitude in the opposite direction, but the force will be the same type. So they'll both be tension forces, or they'll both be normal contact forces, something like that. So define and calculate linear momentum. So momentum is product of mass and velocity. We calculate it using P equals mv. And to calculate resultant force, using Newton's second law, we know the force is equal to the rate of change of momentum. But there is a simplification of that. If mass is constant, it becomes F equals ma. Or if velocity is constant, it comes slightly different as well. So it has a few different forms depending on your conditions, but the one that always works is that force is rate of change of momentum. Next, looking at impulses. So an impulse is the change in momentum of an object, and we can calculate it. So if force is not constant, if it's variable, we have the area under a force time graph. That works. If force is constant, impulse is calculated by doing the force times the time it was applied for. So finishing off looking at collisions. Again, work your way through the section and then we'll take a look. Okay, so principle of conservation of momentum. If no external force acts, the total momentum of a system is constant. That's basically what it says. So again, one last scenario to come up with a question for. So first of all, one-dimensional conservation of momentum. So I'm going to think about gases. So a gas particle colliding elastically with a wall and is traveling in a direction normal to the wall, or 90 degrees to the wall. And the wall is much greater mass than the gas particle, which means the wall is not going to move. Write an expression for the impulse acting on the wall. So if it's an elastic collision and the wall's not going to move, we're going to end up with a situation where the initial momentum is plus mv, the final momentum will be minus mv of the gas particle. So impulse is the change in momentum, which is going to be minus 2mv for the gas particle. So using Newton's third law, the impulse on the wall must be plus 2mv. Okay, so a question for two-dimensional conservation of momentum. So we've got a gas particle colliding with a wall again, but this time it's at 30 degrees to the wall as shown in the diagram, like you can see. So we can apply conservation of momentum in one direction. So there's no force acting vertically, so we can apply conservation of momentum to that direction. And what we get is that the impulse in that direction must be 0. We can't apply conservation of momentum in the horizontal direction because the gas particle is being acted on by a resultant force, just like last time. But if it's an elastic collision, we end up with expressions for the momentum before and after, so we can get the impulse. Therefore, we can get the impulse provided on the wall. All right, so that concludes this video going through the specifications for modules 2 and 3.